Okay, so for this video, we're going to talk about section 3.6 from our course, Introduction to Functions. And many of you may already kind of know what functions mean. So for some of you, this might be review. For some of you, it may not be. It might be a completely new concept or something that you've heard before, but you're really not too sure about what exactly a function is. So we're going to kind of go over that in this section. It's a rather long section in terms of like notes, but it's actually not a lot of writing. There's just a lot of information. So please take good notes so you guys can refer back to these to help you study for the exams. So what we'll be talking about is defining the relation of a function, domain, and range. We'll identify functions, use the vertical line test for functions. Vertical line test is one of our favorite ways to deal with functions. We'll talk about functional notation, and then we will use this to graph a linear function. So all of you know how to graph lines at this point, y equals mx plus b. And now we're just going to kind of change it to functional notation. Okay, so relation, domain, and range. A relation is a set of ordered pairs. So a function is a specific type of relation. So that's what we're kind of going to define these terms as. The domain of the relation is the set of all first components of the ordered pairs. So this is a little bit specific to graphing when they're talking about ordered pairs. I like to think of domain oftentimes, if we were in class going over this, I would ask everybody what they think a function is or what they think domain is. So a lot of people aren't really sure about domain. So this is a very specific, the domain is a relation, or the domain of the relation is the set of all first components of the ordered pairs. Now they're saying a relation is a set of ordered pairs. So normally when people think about ordered pairs, they think about it in terms of, x comma y, like, but it doesn't have to be that way. It could be anything, um, not necessarily x and y on the rectangular coordinate system, but it could also be, in terms of people and birthdays or something along those lines. So don't think ordered pairs has to specifically be x and y, but that's often what we use them as, okay? The range is the relation of the set of all second components of the ordered pairs. I like to think oftentimes as domain as the inputs and range as the outputs, or what comes out of the after you input a value or something. Okay. Now that's a very vague term. So I like to also talk about domain as another way to talk about it is what we are allowed to use in our problem, right? That's a little vague once again, but I'm trying to put it in normal terms. And the output is also, or range is also what we are able to get from our problem. Okay, so again, whatever we're working with, the domain and range, oftentimes people will refer to domain. Domain is associated with the X value, oftentimes, and the range is associated with the Y value, oftentimes. Okay, not saying it's the only thing, but these are all things I'm just trying to associate with you or help you associate what domain actually means. Domain is the inputs. Domain is what we're allowed to use in the problem we're working with. Range is the outputs. Range is what we're allowed to get out or what we're able to get out of the problem we're working with. There's other ways to talk about it, but I think that's enough. A lot of people associate domain with X and range with Y. These are all just ways that we can kind of keep track in our brain of what domain and range actually means. Okay, so determine the domain and the range of the relation. So if I go exactly as is right here, the domain is the set of all first components of the ordered pair. So here's the first component, here's the first component, here's the first component, here's the first component. So they're going to say, let me fix this real quick. They're going to say for this one, domain is going to be, now I like to go from smallest to biggest, and you should as well, -4, 2, 4. Let's see here, -2, we got that one. 4, we got that one. I'm sorry, 2, 4, -4, we got that one, and then 10. So that's the domain. Here's the range. We have, let's see here, -5, that one's gone. Let's go 3, that one's gone. And let's go 9, those are both gone. Now here's the thing, I didn't write 9 twice. You do not repeat your domain and range values. You just simply write, if there's 2 9s in your range, you just write one of them, okay? So we don't like to repeat that, all right? Let's look at example 3, determine the domain and range of a relation. So again, this is not just numbers now. These are, now we're talking about animals, okay, and lifespans, okay? So what I'm gonna do is I'm gonna talk about the domain, okay? So the polar bear, cow, chimpanzee, giraffe, I can't spell, sorry about that, gorilla, kangaroo, I'm just going to abbreviate, and then red fox. I should have abbreviated from the beginning. That is all the domain, because these are all of our first parts of the ordered pair, our input values. You see here it even says input value, and here's the output value. Now we're going to do our range. Now range is represented by the lifespans. So let's see here. What are our ranges? 7, 10, 15, and 20. So what this is saying is that there is a polar bear, a chimpanzee, and a gorilla all live to be about 20 years. A cow lives to be about 15, a giraffe lives to be about 10, and a kangaroo and a red fox live to be about 7. So these are all of the possible lifespans that we can get out of these particular domains or these particular animals. So the domain in this case, once again, is animals, and the range is lifespan. Okay, so once again, this is our inputs. This is what we can get out. Oops, this is what we can get out. Okay, so just keep in mind, it's very straightforward like that. Now, again, for this particular problem, are there more animals than this in the world? Yes, but for this particular problem, the only animals we're dealing with are polar bear, cow, chimpanzee, giraffe, gorilla, kangaroo, and red fox. That's what makes it our domain, because that's all we're talking about for this particular problem, okay? Now here's a special type of relation. A function is a relation in which each first component in the ordered pairs corresponds exactly to one second component, okay? So what that means is if I had a situation like this, if I had a situation of 1, 2, 3, 4, and I had 7, 9, 11, 13, I would say this is my inputs or my domain, and this is my outputs. So this would be, you know, my X's, and this would be my Y's or whatever. But what this is saying is 1 goes to 13, 2 goes to 7, 3 goes to 9, and 4. This mapping works in this fashion, okay? And I'm just making this up, whatever it may be. Now notice that every single one of the inputs goes to only one output, okay? So that's what makes it a function. This is in fact a function. Now, if I come over here and I do this, if I do 0, 5, 7, and then let's say I do, you know, 2, 12, 17, I'm just, again, making this up. We don't know what this mapping is. Okay, we map one value to the next, but this is just the relationship I'm making up. So this goes to 2, this goes to 2, and this goes to 12. Let me get rid of that. Let me just do it like that. So let's see if this is still a function. A function is a relation in which each first component in the ordered pairs corresponds to exactly one second component. So let's look. For 0, does 0 go to only one component? Yes, it goes to 2. Does 5 go to only one component? Yes, it goes to 2. Does 7 go to only one component? Yes, it goes to 12. This is still a function. Okay, but now let's look at another one. Let's say I do this and I do this, and I have 0, 1, 2, and let's say I have 5, 7, 9, 11. So now I'm going to do this mapping. I'm going to go 0 goes to 5, 1 goes to 7, or 1 could also go to 11, and then 2 goes to 9. Okay, now notice here, this is not a function because 0 goes to 5, it only goes to one number. But the moment I hit the number 1, this is my domain, right? This is my range. This is my domain. This is my range, or my inputs and my outputs. The domain, when I go to 1, maps to 7 or it goes to 11. So it could be either one of those. This is what makes it not a function. This is the bad part right here. Okay. So notice here, you are allowed to have more than one domain go to the same range value. That's still okay, but you are not allowed to have one domain value go to two different range values. That's what makes it not a function. So this would not be a function. Now it's still a relation, but it's just not a functional relationship. Okay. So it's kind of important that you understand that functions are very useful in mathematics because there's not a lot of or. So you say, when I plug a 0 in, I get a 2. When I plug a 5 in, I get a 2. When I plug a 7 in, I get a 12. Right here, that is very straightforward. There's no what if you could also get this. So functions feel very deliberate. They feel very straightforward. Non-functions, when I plug a 0 in, I get a 5. But when I plug a 1 in, I could get a 7 or an 11, or I could get a 7, 11, both of them, so that leaves a little bit of doubt. So you're not sure which value you're getting, or you're getting both. So non-functions have that situation happen. So just keep that in mind. That's kind of a good way to think about a function. Okay. Determine whether the relation is also a function. So now we have 4 goes to 9, negative 4 goes to 9. Okay. So what if I drew a little box like this and I put negative 4, 2, I'll just write it as it is. 4, negative 4, 2, 10. And then over here, I'm going to go 9, 9, 3, negative 5. So what I did is I just took all of these values and put them in my ranges, and I took all of these values and I put them in my domain. Okay. So let's do some mapping. So they know that this ordered pair 4 goes to 9. Okay. And then negative 4 goes to 9. Okay. So far, so good. 2 goes to 3. Okay. And 10 goes to negative 5. So since each element of the domain is paired with only one element of the range, it is in fact a function. You don't have to draw it like this. Sometimes you can just look at it and see. Basically, if you see an X value repeated in an ordered pair, and it goes to, two different numbers, you automatically know it is not a function. Okay. So determine whether this relation is also a function. Well, right here, I'm worried. Right there, I see that 3 maps to 2. Okay. Here's 2. But I also see that 3 maps to negative 3. This negative 2 maps to 1, right? So I see that one X value, one domain value, maps to 2 different range values. It could be 2 or negative 3, okay, or 2 and negative 3. Okay, so to me, this is not a function. Okay, now something we're going to learn also is you could also draw a vertical line. Oops, that's a really bad vertical line. You could draw a vertical line like this. Okay, let me do this a little better. You could draw a vertical line like this. And if you can touch 2 values in the same vertical line, that is another way to test for if something is a function. So this is called the vertical line test, but we're going to talk about this a little bit later in the section. Okay. Not much later, it's coming up pretty soon. So here it says, determine whether the relation y equals 7x minus 3 is also a function. Since each element of the domain, the x values, would produce only one element of the range, the y value, is a function. So sometimes you have to look at these problems. There's a couple ways you can do it. We can look at it as a graph. So we could graph this. Let me switch to blue. I like blue better. So we could graph this, okay? And we could go over, I'm sorry, down negative 3, 1, 2, 3. So that's negative 3. And we put, oops, I'll put red right there, okay? And remember, I'm doing the y equals mx plus b technique for graphing, the slope-intercept form. And now we're going to rise 7, 1, 2, 3, 4, 5, 6, 7, okay? And then we're going to run 1. So rise over run. Oops. And I'm going to connect the dots. Oops. Geez, that was really bad. So we have something like that. Now, the thing is, does it look like any X value will produce a duplicate Y value? No, in order for that to happen, it would have to be something like this, right? If we were graphing, because now I could draw my vertical line here, and I could get the same X value or the same Y value. I'm sorry, the same X value would produce two different Y values. So this is why we're going to learn about the vertical line test, because if you know what something looks like graphically, then it's very easy to determine. And you guys are going to have a graphing calculator for this course. So you could just graph this on your calculator and you would notice it's a line, which you should already know. And then you say, oh, well, all lines pass the vertical line test. Since all lines pass the vertical line test besides a vertical line itself, then they're all functions. So the moment I identify this is a line. I know that it's going to pass the vertical line test as long as it's not a vertical line itself. Okay. Let's look at this. Determine whether the relation is also a function. So now we got to start plugging in. Now we have to think, because you may not know that this is a parabola. Now this is a parabola that says when you put an X value in, okay, you put, let's say, you put 2 in for X. Well, it's kind of hard to decide what we could get. How do I say this? What our answer would be for Y. So what I'm going to do is I'm going to kind of just draw something like this. Let me catch up in my notes real quick. So it says, since each element of the domain, the X values would correspond with 2 different Y values of the range, both positive and negative values of Y, the relation is not a function. So what I could do is, this is my domain, this is my range. So this is my, I'm once again going to associate this with my X's and this with my Y's. Okay. So what I'm going to do is I'm going to say, well, if I plug in some number, is it possible, how do I say this? What's the easiest way to explain this? So basically, if I wanted to, I could plug in 1, 2, 3, -1. Let's just start with those. Okay, so if I plug 1 in for X, okay, so if I plug 1 in for X, I get 1 equals Y squared plus 1. Subtract 1, subtract 1. So then I have 0 equals Y squared. Okay, so then that means that this is 0. Okay, so now, because if I square root both sides, you guys remember that, square root both sides, you get Y equals 0 plus or minus. But now let's say I plug in 2 for X. Okay, so now 2 equals Y squared plus 1. And I'm going to subtract 1, subtract 1. So now we have 1 equals Y squared. And we square root both sides. So this becomes plus or minus 1 equals Y. So that means I have to put -1 or 1. So yes, 1 maps to 0, but now 2 maps to -1, and it also maps to 1. And this will happen for 3, for 4, for 5, for 6, for any number we pick. This will happen from here on out. Okay, so we only needed one case to happen, but this would just happen repeatedly because of the way that square rooting works with plus or minus. So this is not a function because right here, I instantly see that my 2 could be -1, or my 2 could also be 1. So this is actually a parabola that is shifted. I think it's like this. Yeah, this is a sideways parabola, basically like this. Oops. Some kind of parabola like that. Okay, where it's sideways and then we draw the vertical line test. Okay, so basically, we know that this is not a function. Okay, so the best way to test is if you know what the graph looks like for functions, you just draw vertical lines anywhere you want. And if you ever touch the graph more than once with that vertical line, you say it's not a function. So I could give you, let me do this. I could give you this, I could give you this, I could give you this, and I could give you this. So let's say I draw this graph. Let's say I draw a line. Okay. For this one, let's say I draw a circle. For this one, let's say I draw an ellipse. And then for this one, let's say I draw a parabola. Okay. I can't draw too well. Sorry about that. Okay. So let's draw our vertical lines. So I can draw a vertical line anywhere and I'll only touch it once. So this is a function. See how easy that is. Here, I draw a vertical line anywhere. I'm going to touch it twice, except for maybe on the sides, I get tangents, but boom, right there, vertical line. These are all technically lines. I don't want to go through and do it, but you guys get the idea, right? So you can draw a vertical line anywhere you want. And if you can touch the graph twice, it is not a function. So this is not a function. It fails the vertical line test. Okay, boom, not a function because I touched it twice, here and here, here and here, not a function. Okay. However, this one, I draw a vertical line here, I'm okay. I draw a vertical line here, I'm okay. Here, here, here. Anywhere I draw a vertical line, I only touch the graph once. So this is in fact a function. So a parabola is a function. Now, this is oftentimes referred to as a vertical parabola. And then this one that I drew, oh, I erased it already because I drew it really ugly. That one was a horizontal parabola, or I often call them sideways parabolas versus up and down parabolas. So the vertical line test is amazing. Look, boom, vertical line, that's a function. So it's very easy to test something if it's a function, if you know what the graph looks like. So once again, you guys have graphing calculators. We'll talk about that later on how to graph on the calculator. And then we can go from there. So use the vertical line test to determine if the graph is a function. Okay. Vertical line, vertical line, vertical line, vertical line, always a function. So yes, a function. So again, I want you to see how nice this is. So here's an ellipse. Boom, here I could have drawn it there, 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 there. Any of those places, it shows me it's not a function. But it only has to happen once for it to not to be a function. But I have an infinite amount of ways I could draw it, okay? So now let's talk about functional notation. Okay, so functional notation is basically taking this notation y and rewriting it as f of x. And it does not mean f times x. So this does not mean f times, oops, f times x. That is not what it means. It literally reads f of x. So what happens to f based on what x is? Okay, and that's what we do anyway. If I say y equals 2x plus 3, and I say what happens, what if x equals 2? So then we say y equals 2 times 2 plus 3, so y equals 7. What functional notation says is f of x equals 2x plus 3. And now instead of writing what if x equals 2, now I get to write f of 2 equals 2 times 2 plus 3, which is 7. So personally for me, functional notation is just better. But when you're writing it like this, f of x, you're implying, you're telling someone that this is in fact a function. F of x is a function. Again, it doesn't have to be, but for most of algebra, that's what they imply by writing f of x or h of x. You're implying that it is a function. So this is the notation we like to use to imply it's a function. Again, it doesn't have to be that way, but we like to do it that way in math. So it's just a faster notation. So now I could say f of negative 2, and then that just means 2 times negative 2 plus 3. So this becomes negative 4 plus 3, which is negative 1. Okay, but remember, you are building an ordered pair. This right here would be the point 2 comma 7, right? Here's my y value, here's my x value. This right here would be the point 2 comma 7. Here's my x value, here's my y value, here and here. So functional notation tells you, maybe I should use red. Functional notation tells you the x and y coordinate. Here's the x coordinate, here's the y coordinate. So I have an ordered pair of negative 2 comma negative 1. So it's really nice and convenient to work with, okay? So find each function value. So let's use this type of calculation. Oh, I forgot to read this to you guys. So this notation means that y is a function of x, or that y depends on x. So just to reiterate what that's saying is whatever is inside of here is the independent variable, and whatever is outside is considered the dependent variable. For this reason, y is often called a dependent variable and x the independent variable. And remember, we normally in math, for a very long time, we use y equals f of x interchangeably. Whenever you see an f of x, you could probably call it y, and whenever you see a y, you could probably call it f of x. That's just kind of a general rule of thumb we use in math. These are the very common notations. They normally use f of x, g of x, or h of x. These are very common ways to name something a function. So once again, in general, this is just our notation that we really like to use, and we're going to use it throughout the course from here on out. So if you're asked to find function values, all you do is what I just did here. If they say find f of 2, all they're saying is replace x with 2. So we're going to say f of 2 equals, and then I'm just going to say 4 times 2 minus 1. So we get 7. And once again, that's 2 comma 7. We found the x and y coordinate 2 comma 7. Now here they say g of negative 3. So we do g of negative 3 equals negative 3 squared minus 2 times negative 3. I like to use parentheses whenever I plug in, especially with negative numbers, so I don't mess up. So I would recommend you guys do that as well. So this would be 9 plus 6, which is 15. So we just found the x coordinate negative 3, or the point negative 3, 15. Let me just go and double check I'm not making any silly mistakes. Okay, so here we are. Okay, so far so good. Hopefully you guys are doing okay. Remember, if I ever start going too fast, I don't have an audience that I'm necessarily speaking to live. So, go ahead and pause the video while you catch up. Okay, so number 18, given the graph of the function f, find each function value by inspecting the graph. So something very useful is, now that we know what function notation means, we can interpret what it's saying graphically. So when they say f of 5, what are they saying? They're saying, tell me what happens to y when x is worth 5. So f of 5 means, okay, tell me, and this is paraphrasing, right? Or not paraphrasing, but this is, very loose math talk. Tell me what is happening to f or y if x equals 5, okay? So all of this means this statement, basically, okay? Again, I'm using it loosely, but that's a good way to think about it. So when I say f of 5, I'm saying, what is my y coordinate? What is my height of my graph when x is 5? So I come over here and I go to x equals 5. So here's 1, 2, 3, 4, 5. So right here at 5, I have to look down. There's nothing here, okay? So now I look up. What's up here? What's height is this right here? That is a height of 4. So I now have that when x is 5, y is worth 4. So I have a coordinate 5 comma 4 on the graph. So this notation right here is actually telling us xy coordinates, 5 comma 4. You just have to find the y coordinate. Now f of 1, once again, you know what, I can write that over here. Let's just do it over here now, because now we kind of figure out how to do it. So f of 1, I'm right here now. I go and I look at, when x is 1, what is the height of my graph? So I go over to 1 and I go up right here. It's at 2. So we say 2. So we have the point 1 comma 2, the xy point. Now we go negative 1 and it's 4. So we say negative 1 comma 4. Now we have negative 6. That would be negative 5. That's right here. So negative 5. Okay, so hopefully that makes sense to you guys. That's how you can look at a graph and know what this means, f of 5. What does that mean to say f of 5? It means, what is my y value when my x is worth 5? So it turns out my y value is, in that problem, 4. So here I'm going to write negative 6 comma negative 5. So we now have these coordinates, okay? And we could do it for every single one of these. We could tell the x value, okay? And then you could find the y. Now, the other thing we could do is, what if I said f of what would give me, let me see what's a nice one. F of what would give me, 7. Okay, so now what am I saying? I'm saying what X value would give me a height of 7. So now I got to go look, where's my height of 7? Well, that's right here. That's a height of 7, right? Here's a height of 7. So what's my X value? 6. So I would say f of 6 would give me a height of 7. So we have the point 6 comma 7. Okay, so hopefully that helps you guys understand what you can do graphically by looking at it and what this notation means when they say it. Okay, so this is kind of just a little review just to make sure you guys are aware of this. A linear function is a function that can be written in the form f of x equals mx plus b. You guys know this as y equals mx plus b. This is slope intercept form. And you hopefully have been using this for a while, where we know that m is our slope and b is our y-intercept, meaning where does it cross the y-axis? Okay, so this is something that we're just now converting to f of x equals mx plus b. No big deal, just changing the y to f of x. So let's just look at this. It says graph the function. So once again, I'm going to go to my y-intercept. Remember, when you guys are doing this, you always go directly to your y-intercept first. Put a point right there at -2. Then you use your slope, m equals 3. But remember, slope is always a rise over a run. How far up or down you're going versus how far left or right you're going. So in this case, m is equal to 3 over 1. So we go up 1, 2, 3, and run 1, and then we connect the dots, and we have that line. You see the same line that they drew, I could draw it. Okay, so that's pretty much it, just making sure that you guys know how to do y equals mx plus b. Very common technique. I think that's going to do it for this video. It's about 30 minutes, so please give it a look, and I will see you in class.